How are you guys doing? Today is the second we are recording, and I've got great news for you. The great news is that it's Thursday. More great news is that we're learning about drawing Lewis structures. Lewis dot structures, not of atoms, but instead of molecules. Now, could everyone give me let's go with a six in the chat if, hmm, I don't want to say if you're having a good day. I like it. Yeah, just give me a six in the chat if you're here. Nice, 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 nice. Okay, great. I'm happy to see that. I'm happy to see that. Um, and then I'm also happy to see in my background stuff behind me. In particular, this right here. This is a trophy that I won in 1989. I was six. It was for the fall fun run. Oh, someone hit me with a 6-7. This is my response to 6-7. I don't, I'm old. It happened. It happens fast. So buckle up, everyone. Um, I have a son who's in fourth grade and he plays baseball. And so everyone on his team, no matter what, like one person will say, oh, like the score the other day, they ended a game in a tie, which I was like, this is baseball. Baseball does not end in a tie, which was my response whenever I was watching the Green Bay Packers play the Cowboys. I was like, this would never happen in baseball. At any rate, the score ended 7-7, and so then all the kids were like, the game was 6-7 at one point. It was 6-7, 6-7. Anyway, that's that. Okay, so today what we are talking about is we are going to be drawing Lewis dot structures. I've got the slide deck up on our Canvas page. The file name is Chem 1310 week 6 day 2, and I'm going to jump right into it. We got three poll questions. I think we got three. Today we're not doing any scanning of anything or taking pictures, but I really appreciate how everyone did that, and thank you very much. I was a little bit kind of test driving that as to see like, is this something that's technically like too much of a burden to try and to do? And it seemed like most folks were able to do it in a pretty short period of time. So it wasn't like it took 30 minutes for everyone to draw a picture or to write out their answer and then draw and then take the picture and upload and everything. So there were quite a few steps, but it seems like everyone got through it pretty seamlessly. So thank you for that. Okay, now just have to move that there, move that there, move that there. Okay, so how to draw a molecule's Lewis structure. The other day we were talking about polarity. We were talking about classifying molecules as ionic, as polar, as nonpolar. Now, if you remember, whenever we talked about an ion, basically you can split every compound into either being an ionic. Oh, Joel. You can split them all into being either ionic or covalent. Could somebody give me the range of electronegativity differences for a non-polar covalent compound? What's the electronegativity difference? That or what's the range of the electronegativity difference for a non-polar covalent compound? Perfect. Less than zero point 0.5. And then for a polar, could somebody give me the range for that? 0.5 to 2. And I like how you responded. It's 0.5 to 2. So that includes 0.5 and it includes 2.0. So that gives us anything with a electronegativity difference of 2.0, or sorry, greater than 2.0 is an ionic compound. All right. Now, to draw a molecule, this to me is one of the most central parts of chemistry because it's a way of taking something like this, NH3, and visualizing it and saying, okay, well, yeah, I've got a nitrogen and three hydrogens, but how are they connected? And, you know, could anyone tell me in the chat, what does this line between the nitrogen and the hydrogen, what does that represent? It's a bond, but what does a bond represent? One pair, two electrons, perfect. One pair of electrons, great. Now, the alternative to that, so this would be, you could call this a shared pair. And then if I put a pair of dots over this, and I drew an arrow to that, what does that represent? Yeah, it represents two electrons, but what's another term we use for those? Perfect, a lone pair. So typically, I had this question the other day, and it was, is there ever a time whenever you see electrons as individuals? Yeah, there is. And it's not to say it's uncommon, but it's a little bit there. It's less stable. So it's something that will happen in a very, very short period of time because every compound wants to reach a level of stability. And so typically, whenever you're talking about electrons, we have our octet rule. Everything wants to gain or lose or share electrons to get to eight electrons around it. But usually we'll talk about electrons as either a pair, a shared pair of electrons, or a lone pair of electrons. Now, this lone pair, I'll try to not use this term very often, but in the event that ever I say an unshared pair, well, I'm talking about electrons that aren't shared between anything. Could everyone give me a forward slash in the chat if you understand what an unshared pair versus a shared pair of electrons means? Great. Years ago, I got into a very, very um, intense discussion and debate about a forward slash versus a backslash. And the person I remember telling me, what everyone has typed into the chat this person was telling me that that's a backslash. And I was like, no. And they said, yeah, it slides back. And I was like, you're wrong. Anyway, so whenever we talk about drawing a molecule, we have to understand valence electrons. How many valence electrons are around a given atom? And this is something that we can simply pick up from the periodic table. Now, this shows the Lewis structures of all these different atoms. And here, what we've got is, well, one valence electron around hydrogen, two around beryllium, seven around fluorine. Now, this does kind of relate to our discussions of electron configuration. So that is a relevant part of this, but that's not something we're going to be going back to for this specifically. But I think that it is helpful as kind of like a review to think for yourself, well, how many electrons does this fluorine have in the p subshell? Okay, well, if I can remember, if I can construct my electron configuration, it'd be 1s2, 2s2, 2p5. Okay. Now, what we're focused on, though, is we're focused on seeing something like fluorine and saying, okay, fluorine, it has seven valence electrons. We know that fluorine wants to kind of follow the octet. And so what it's going to do is it's going to gain one more electron. How's it going to gain it? Well, it's either going to gain it by basically taking it in the form of an ionic compound, or it's going to share an electron with another atom in the form of a covalent bond. Okay. Could everyone give me the letter W if you can see how, yeah, these things are connected? Yeah, these things are related. Okay, great. Now, this, I'm going to try to keep myself, I'm going to try to keep myself as focused as possible on drawing Lewis dot structures. I'm bringing this up as context. This slide, let me clear all the writings on here. This slide right here, with what you see right here, is extremely valuable information. Now, How can you kind of put this information together? Well, by referencing the periodic table. But more than that, this is valuable because of the fact that we'll be able to use these figures, use these structures to build a molecule and to draw a molecule as a whole. Okay, so if there's two things that I need you to be moving forward with from here, it is the content on this slide, and I'll toggle back and forth. I'll go back and forth on this. But the content on this slide, and it's important to know the octet rule. Now, what do we know about rules? And what do we know about, well, sorry, rules are not necessarily meant to be broken, but it's good to know the rules, it's good to know the law, but it's also helpful to know exceptions. There are some exceptions to the octet rule. I'm going to say the octet rule is everything wants to get to 8 electrons. Okay. The exception is, well, not everything. Actually, let me rephrase that. Rephrase that. Some things can exceed the 8 electrons, and some can go under the 8 electrons. Now, with that in mind, if you look at your noble gases, is there a noble gas, and add the symbol if you see it, is there a noble gas that does not need to have 8 electrons around it? Perfect. Helium. So we kind of already know an exception to the octet rule. One exception, go under, I'll say, is helium. Great. Now, what I'm going to do is I'm going to say basically everything blocked off in red is under 8 electrons. Everything that I've highlighted there, those first few atoms, including boron, they do not need to get those 8 electrons. Now, I'm going to go on to say, basically here, these can exceed 8 electrons. And when you're looking at this, I think it's a pretty fair thing to look at it and say, 8 electrons, things that exceed, and things that actually want to reach that octet, there's actually maybe not a whole lot that wants that 8 electrons. And I would argue with that, and I would say, well, that is fair. That is a fair assessment. But I would go ahead and add a little detail, and that is not common. So it's not super common when something exceeds the octet. Okay. Now, with that in mind, there's a couple of things, and we'll look at an example today, but there's a couple of elements that I would say, okay, these are going to be good ones for you to know as ones that exceed the octet. Compounds that contain phosphorus, sulfur, and chlorine. These are all elements that they like to exceed the octet. So if you're like, okay, what's my list for things that go under the octet? Well, I would go with boron is under. Most of these other compounds like lithium and beryllium, they're going to form ionic compounds. Yeah, they won't have to reach the octet. They won't have to have 8 electrons around them. But in terms of covalent compounds, boron is your one that's going to be under the 8 electrons. Then phosphorus, sulfur, and chlorine are the ones that are typically going to exceed the octet. So I would like you to kind of file those three, phosphorus, sulfur, and chlorine, as okay, whenever I see them and I see something that, oh man, that looks like it breaks the octet, that's fine. Can you give me a Y in the chat? Just the letter Y in the chat if you're like, okay, cool, I can remember those four elements as being my major exceptions. Okay, cool. Now, just a minor aside, my background is in biochemistry. And I remember taking my first few chemistry classes and being like, here's the periodic table, and thinking to myself, oh my gosh, there's so many elements. There's like, at the time, there were like 114 or 112. Now there's 120, I think. Um, and then I got to my first biochemistry class, and it was like, hey, remember the periodic table? We don't use the entire periodic table. That's not biologically relevant. There's like 10 elements that are biologically relevant. So we're going to focus in on those. And those big ones are carbon, nitrogen, oxygen, and maybe to a lesser degree, fluorine. But carbon, nitrogen, oxygen, and sorry, hydrogen, those are your big four are that you're going to see in compounds more than anything else. Okay, so now what we're going to go through is the deliberate and pretty, what I hope to be clear steps on what you do whenever you're confronted with a formula. So the first thing that you need to do whenever you see a formula provided to you, and just 1 second while I pause my screen so that I can make sure that I work through an example and then don't use one that I'm going to seal. Okay, wait. Rats. Sorry about that, everyone. Let's see, we've got, nope, Joel. Okay, yeah, stop sharing. Thank you, computer. Okay, cool. We're going to use one molecule as our example to build up and follow these rules. And lots of this information I'll provide to you just right off the bat, and you don't have to toggle back and forth to see a periodic table or anything like that. So your starting point. Let's say that we are trying to draw the Lewis dot structure, or the Lewis structure as it's commonly known, of CH4. CH4 commonly known as methane. The first thing that you need to do is identify the atoms, or the elements, and how many of each there are. Well, I see 1 carbon, 4 hydrogens. Now, after you have the atoms and count all of their electrons, so that's the next thing that we have to do. Find the central atom. Okay, so I'm going to jump back to this slide right here. We've got a carbon atom with 4 electrons. And then we've got 4 hydrogens, each with 1 electron. So we've got, erase all that. 1 carbon equals 4 electrons. 4 hydrogens equals 4 times 1 electron, or 4 electrons. So our grand total of electrons that we have to work with is 8. Can you give me an A in the chat if you agree with that and follow where I got all that from? Excellent. Okay, so the first thing that we have to do, sorry, not the first thing, but after we've counted up our, I'm going to add this out here, 8 electrons. I'm going to erase this, where that, yeah, I'm going to erase that. I'll leave this one just because there's a little bit more to it. We've got 8 electrons total to draw. The first thing that we have to do is we have to identify our central atom. Okay, I got a private message. How did I get the 8? Well, I got the 8 because I have 1 carbon, and carbon has 4 valence electrons, which is what we see right here. So 1 carbon equals 4 valence electrons. We have 4 hydrogens. So here's our 4 hydrogens. Each one of those hydrogens has 1 electron. So 4 times 1 electron is 4 electrons. So those are the 4 electrons from hydrogen, the total 4 electrons from hydrogen. And we had 4 electrons coming from carbon. So that's how I got to 8. Can whoever messaged me that question confirm? Yes, I got it. Okay, cool. So the next thing that we need to do is identify our central atom. Now, one thing that's important to know about this step is, and lots of other things on the, and when it comes to rules and drawing molecules and rules in chemistry, hydrogen is super common, but it's also, it is an exception. So it breaks most rules. So just keep that in mind. Now, with that said, our two atoms, our two elements that we have are carbon and hydrogen. So what we want to do whenever we see this prompt, find the central atom, what we are looking for is the least electronegative element. It is also, so this statement is also true. It is the one that is typically farthest left, and just put L on the P table. Okay. And in addition to all that, it is usually the first element written in formula. Okay. Now, with that in mind, hydrogen presents an exception. So you can almost ignore hydrogen whenever you're trying to identify your central atom. And then you basically say, okay, if I'm ignoring hydrogen, then my central atom is going to be carbon. Okay. Now, applying some of these other ideas, the least electronegative element. Okay. So what is our trend? Or we know a trend when it comes to electronegativity. Could anyone add to the chat the symbol for the most electronegative element? Fluorine. Perfect. Fluorine is the most electronegative element. When it comes to the trend of electronegativities, that little rectangle that I drew there represents my periodic table. Electronegativity increases. It goes up as you move from the lower left to the upper right. So lowest, highest. Okay, so that's a good trend to remember. Next up is typically farthest left on the periodic table. Well, hydrogen is going to be the farthest left on the periodic table, just looking at this right here, compared to carbon. But again, hydrogen serves as a good exception to lots of rules. And then the last thing, usually it's the first element that's listed in the formula. So this would be something that, yeah, it's helpful whenever you look at this. And more times than not, for the formulas that we will do in this class, this is going to check out. That's going to be just fine. Where it's not going to help is if you get a word problem that says you have a compound made up of 4 hydrogens and 1 carbon. Well, that doesn't help. You don't have the formula there. You can piece together the formula, but if you wrote H4C, that's not going to help you with this rule right here. So you've got to kind of juggle these 3 details, and you've got to keep in mind that exception. So with that said, can everyone tell me in the chat, what is our central atom for this formula, CH4? Wonderful. Carbon. You're absolutely right. It's carbon is our central atom. Now what we're going to do is we're going to go to our next step. So we're drawing CH4. Our central atom is carbon. Next, we're just going to draw all of our other atoms around that central atom. Okay. Now, before we do this, I'm going to give you two options, option A and option B. And I'm going to put carbon down first in both cases. One thing that's important to think about is that carbon is the central atom. And if you keep the octet rule in mind for this, it's going to help you out quite a bit. One option is I'm going to draw H, 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 H. I haven't drawn any electrons, I haven't drawn any bonds, but I'll give you that option, and then here's another option. Before you place anything, let's just do a little survey. Do you think that it's A or B? Okay. Okay. I'm seeing lots of A's. I like it. There's sort of you kind of have an intuition because we've talked about these rules and maybe you've seen CH4 before. Maybe we looked at it last class. Um, you have almost an intuition of, okay, well, given the two options, I'm leaning towards this. Now, this next step. So I'm going to go with A and I'm going to show you B as well. We've got C, H, 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 H. This is kind of a bare bone structure. And now is whenever I fill in any spaces, I fill in any gaps or voids. Okay. Um, done, 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 done. Okay. Now let's dissect B for just a moment. And I'm going to switch colors on my ink here. Could anyone add to the chat how many electrons are represented by what's shown in the red circle there? Two. Okay. Now, in this red circle, how many electrons are shown there? Two. Great. Um, do these add a yes or a no, or y or an n? Do the two electrons that are shown in this red circle, are they owned by one element or by one atom? No, they're not. They're shared. They are shared between carbon and hydrogen. So when we circle carbon here, and I'm just going to circle the atom and those electrons, that carbon says, I have two electrons. And you know what? Whenever I switch the circle and I circle the hydrogen, how many electrons does that hydrogen have? Two. So this is where one of the places is kind of tricky. Um, these two electrons, they are shared, but they're double dipped. This carbon says, I've got two electrons here. This hydrogen says, I have two electrons here. They are sharing those two electrons. They're both kind of showing ownership of them. Could you give me a Y or an N in the chat if you follow that? Great. Now, when hydrogen has two electrons, does it have eight electrons around it? Y or N to the chat? No. It's breaking the octet rule. But give me a 1 in the chat if that's fine. Or a 2 if it's not. Great. Hydrogen is fine with two electrons. Now, with that in mind, how many electrons does this hydrogen have? 4. Hydrogen doesn't need 4 electrons. Hydrogen is happy with 2 electrons. Okay? So that's one of the reasons that this model is a little bit flawed. How many electrons does this carbon have? 4. Carbon wants to get to 8. It rolled in with 4. It brought 4 of its own. Why would it share some of them in order to stay at 4? In addition to that, I mean, what you could do is you could look at it and say, oh, well, let's go on to the next slide. And Or not, sorry, got ahead of myself there. This carbon only has four electrons. Well, what if I put one, two, three, four? If I put two lone pairs of electrons on there? Well, how many electrons does this carbon have? Now, eight. Oh, carbon wants eight though. But we've got two different options. This option where our hydrogens are happy with two electrons. And then if we circle our carbon with all its electrons, how many electrons does this carbon have? Eight. Okay. So in both situations, well, carbon is happy. Hydrogen in this model B, I'm going to put it at sad and happy because, well, this hydrogen's fine. But could anyone tell me how many electrons are represented in this model? 12. Now, if you're sitting at home and thinking, where did 12 come from? 2, 4, 6, 8, 10, 12. Could you give me an 8 in the, or give me a plus symbol in the chat if you follow that that's where the 12 came from? Okay, now I'm going to ask you this direct question. Did we have 12 electrons to draw? Y or N to the chat? No, we didn't. So this, we made up electrons. We made four electrons out of nothing. I'll just say we made four electrons up, which ultimately is a not possible. Okay. Now, if we look at model A, I already circled the carbon. That carbon had eight electrons. I'm going to circle the whole molecule. How many electrons do I have here? Eight. So this one's good to go. Could you give me a Z in the chat if you follow how these two models are different? One's okay and one's wrong. An X in, let's go with an M in the chat if you don't follow. Okay. So now what we're going to do is we're going to go ahead and fill in the other rules. Now, one of the things that's a little bit challenging is that these rules, as we go on, don't apply to this specific molecule. They will apply to other molecules, but with this one, we drew four lines representing single bonds. Each single bond represents two electrons, so we drew those eight electrons in, and we were good. Will it be the same way for elements with more valence electrons than carbon and hydrogen? Great question. We're going to basically treat them the same way. The question is, and if I understand this correctly, well, what if something has more than four or one valence electrons? Will they still aim to get the octet, or will they still aim to be under the octet? Well, we've got our exceptions to the octet here. Phosphorus, sulfur, and chlorine. Well, phosphorus, sulfur, and chlorine, they all have more valence electrons than carbon, and we're going to do some examples with each one of those. But these are ones that are capable of exceeding the octet. And in just a little bit, we'll get to a molecule with tons of electrons, okay? So I hope that will answer that a little bit more clearly in just a moment. Okay, so I've drawn my two models. Then this next step and these next series of steps are going to be applied to some of these larger molecules. After we've drawn our individual lines connecting each one of our atoms, we're going to place our electrons on our outside atoms. And then we're going to place them on our central atom. And we're going to basically try to get each atom to have a complete octet. Okay. And then, as you need to, add a double or a triple bond. So the first thing that we're going to do is, and this step, this step, this step, and this step. So these last four steps, I'm going to come back to them when we're using them. For CH4, we didn't need to use them because we used all of our eight electrons up. Could you give me an R in the chat if you say, right on, I follow. Okay. So we're drawing water, H2O. The first step is to identify how many in which atoms are you using. Well, we've got two H and one O. After you have the atoms, count all of their electrons. Well, there's two hydrogen atoms, one electron each, two electrons. Oxygen. I'll jump back. Oxygen has six electrons. Okay. Now we need to find our central atom. Well, we've got hydrogen and oxygen. And sometimes this might appear a little bit like, oh, well, that's kind of odd because, well, is it central? Yeah, I guess. I mean, yeah, I guess. You could draw H2O where oxygen is the central atom. And oxygen will be the central atom because hydrogen serves as our exception. So hydrogen's basically never going to be the central atom. So we've got our central atom of oxygen. We're going to draw our other atoms around that central atom. Boom. Oh, wait, I jumped a step. I apologize. My other atoms, hydrogen, hydrogen. I'm going to connect. Done, done. At this point, give me a Y or N in the chat. Are each of the hydrogens happy? Yeah. And my subtext or my preface there is that, well, hydrogen only needs two electrons. So each of these hydrogens, they're like, I'm done. Did my work. I'm good. I brought one electron and I shared it. Okay. So each hydrogen is good. Now, follow-up question. Give me a P in the chat if oxygen is good. Good. No responses. It's not, because oxygen only has four electrons around it. Okay, so if we add these numbers up, here's our total number of electrons that we could draw. We had 8 electrons. What I like to do is I like to keep track of my electrons. So I'm going to go ahead and do this little accounting table. Total electrons is 8. Then I drew two, I'm going to write SB, single bonds. Each one of those single bonds is 4 electrons. So 8 minus 4, I'm doing 8 minus 4 because I've drawn those bonds. So I have 4E left to place. Okay, so now I get to this and give me a 1 on this, a 1 in the chat if you follow, and a 3 in the chat if you are lost. And if you are lost, please follow up with a private message as to where you maybe got lost. Okay. So the next step is to place my electrons on my outside atoms. Could anyone add to the chat the symbol for my outside atoms? Or the letter for those outside atoms? Oxygen is central, so hydrogen, yeah, perfect. Now, my question is, if I said, okay, well, I've got 4 electrons, if I did this, here's 2 and here's 2 more. Is that right? No, it's not. Because we know that hydrogen, I'm sorry, does not like to have more than 2 electrons. So I'm going to erase those. So in this step, it's like place your electrons on your outside atoms. Well, that's not a. I'm going to go ahead and qualify that and say, if suitable. Then, so I still have these 4 electrons left to place because I couldn't place them on my outside atoms. Now what I'm going to do is go place my electrons on my central atom. My central atom is oxygen. So let's say that I do this, and I do this, and this. Okay, so in this case, I tried it, and you know what? That looks like, well, how many electrons are now around oxygen here? 8. How many electrons does oxygen want to get? 8. So I would say that I had 4 electrons left to place. I placed them around oxygen, and now I'm down to 0 because this represents a pair of electrons. This represents a pair of electrons. Now, my next thing is, and oxygen here has, remember, a bond represents a shared pair. So this oxygen has 8 electrons around it. Now, is this the correct model for oxygen or for water? It is. It's great. Is this exactly what you'd see if you did a Google search for Lewis structure of water? No, it's not. What makes it different? Well, the only thing that makes it different is what you'll see is you'll see water looking like this. And the reason you'll see water looking like that is because lone pairs of electrons, they occupy more space. And what those are going to do is they're going to push that or push these shared pairs of electrons. And we're going to get into this a little bit later when we talk about molecular geometry. But for the purposes of what we're doing, building a structure, if you see this, consider that, okay, I'm good to go. This, I'm going to say, is more realistic because it talks about what's going on, or it kind of illustrates more realistically what's going on. Okay, taking into account the CH4 and H2O on a scale of 1 to 5, 1 being I've got this, and 5 being Lewis who? Tell me you're just thinking about these two and going through those steps. Okay, I'm happy to see lots of ones. That's great. And I'm good. Ones and twos. Awesome. Okay, so now what we're going to do is we're going to progress to draw things that are a little bit more complicated. We're going to follow the same process. I'll toggle back and forth between the slide that we're going to be looking at and, man, I shouldn't have put this slide right here. If you have this slide deck open on your computer, then I would hold this slide open because it's going to save you a little bit of time. But I'll be going back and forth. Okay, I got a private message question for what does SB stand for? This SB right here, single bond. I drew 2 SB or 2 single bonds, and each single bond represents 2 electrons. Okay, now we're going on to draw NH3. So NH3. Could anyone tell me what is our central atom here? Nitrogen. Great. Nitrogen's our central atom. That's a good jump off place because it's like, well, we've got, well, nitrogen or hydrogen. Hydrogen's basically never the central atom. So we're going to go with nitrogen. Okay, now I'm going to draw my general structure. Or I'm going to start out with my central atom. And then I'm going to go back to nitrogen has 5 valence electrons. Okay. Now, if you're thinking about this, we might have a little bit of a challenge here. So 5 electrons, and then hydrogen rolls in with, well, there's 3 of them, so 3 electrons. My adjacent atoms, or my outside atoms, are H, H, and H. I've drawn all of the atoms that I need. I have 8 tote electrons. Now I'm going to draw single bonds. 1, 2, 3. So now what I'm going to say is 3 SB, and I'm going to subtract that number of electrons. each single bond represents two electrons. So we're talking about -6 to represent those three single bonds. Okay. So 8 minus 6, 2. Can everyone confirm yes or no? Okay, yes, you followed what we've done so far. Wonderful. So what we did was we got our total number of electrons by looking at the periodic table and saying that nitrogen has 5 valence electrons and each of my hydrogens has 1. There's 3 hydrogens, so we've got 3 electrons. So that's where my 8 total electrons came from. I placed my central atom, which is nitrogen, because hydrogen's never going to be your central atom. Then what I did was I drew single bonds here, here, and here to connect nitrogen to hydrogens, or the nitrogen to the 3 hydrogens. Each one of those lines corresponds to 2 electrons, so I drew 6 electrons. That's where this 6 came from. So now I've got 2 electrons left. My next step is to go to outside electrons. Okay, I've got 2 electrons to place, but am I going to skip over that? I am, because my outside atoms are hydrogen. So we skip over hydrogen because hydrogen is happy with 2. This, and this are all hydrogens that are good to go. They all have 2 electrons. Okay, so I'm going to erase this, and this. But I'm still left with 2 electrons. So after I've skipped my outside atoms, those being the hydrogens, what am I going to do? Where should I put those last 2 electrons? Just like we did with water, we put those electrons, if they don't go on the outside atoms, we put them on our central atom. Boom. Now the next question is, so I'm going to say -2, and this is a LP, or a lone pair, on nitrogen. 2 minus 2, 0. Have I drawn all 8 electrons, a Y or an N, to the chat? I have. Now, is there anything else I need to account for here? No, I'm good. This structure right here, perfect. This is a compound or a formula known as ammonia, not to be mistaken with ammonium. Are you going to be tested over that? Are you going to be expected to know that name? No, you're not. But does anyone know of anything that has a lot of ammonia? Yeah, cleaning products. I just got a fantastic question as a direct message. Would the lone pair push the two hydrogens next to it? Yes, it would. Because this lone pair of electrons, I always kind of think about it as they occupy like a balloon shape. And has anyone ever done like a balloon animal or anything like the um and I hope that that was clearly communicated. Has anyone ever done, yeah, people have. Okay. It was unnecessary to pause for that. I apologize. Um, so I always kind of think about this would be like a regular balloon. Reg balloon. And this would be like a I guess tube balloon. I don't even know what those are called. Party balloons? I don't know. Balloon animal balloon. Boon balloon. See, this is the challenge whenever I'm writing on the screen. You guys see words that I can't spell. I'm just happy I don't have to write committee or communicate. Those are ones that I'm like, should I put like 5 M's in there? Okay. So, yeah, this regular balloon, these 2 electrons, this lone pair of electrons on nitrogen, they use force to kind of, and actually, let me ask this question. What do you know about if you have 2 negative things coming towards one another, what are they going to do? And the word I'm looking for starts with an R. They're going to repel. So this lone pair of electrons, they're going to repel here and here. So really these, let me draw this a little bit differently. It's going to look a little bit more like this. And again, we're going to revisit this stuff in a couple of days when we talk about geometry. Okay, 1 to 5. Where do you think you are? 1 with I'm good, a 5 being I'm lost. Okay. Okay, so I'm seeing kind of the average number has crept up a little bit. What I'm doing is I'm doing this exact same set of rules right here. And that set of rules is basically spelled out here. My point of reference, my biggest reference point is this slide right here. This tells me the number of valence electrons that each atom is coming to the party with. Okay, so now what we're going to do is we've got our first poll question. And I'm going to launch the poll. Polls. And if somebody answers before they see the question, that means that they probably already looked at the slide deck. Okay. How many total electrons do we need to account for when drawing this molecule? And I'm fine working through this together. Okay. So our molecule is SF4. San Francisco 4, not really. Sulfur tetrafluoride. If you're feeling bold, you could add to the chat, is this a ionic or a covalent compound? So what I'm going to do is I'm going to go back because the first step that I need to do is answer this question. Sulfur rolls in with how many electrons? Fluorine rolls in with how many electrons? Some of these you'll get so familiar with that you're like, I know exactly. Sulfur rolls in with 6 electrons. I got a private message, covalent. You are absolutely right. Well done. Okay, sulfur is rolling in with 6 electrons. Each fluorine is rolling in with 7 electrons. The ones that I kind of become like muscle memory would be fluorine, as an example. Because fluorine has 7 valence electrons, its preferred thing to do is to pick up 1 electron. Only 1. Which, if it only needs 1, that means that it's got a, sorry, it if it only needs 1, then it's going to roll in with 7. So it has 7, sorry, it has 7 valence electrons already. It needs 1 more to get to a complete octet. I'm sorry about that jumbling set of words and that poorly sentences. Stop, Joel. Sentences bad. Okay. Now we've got 4 fluorines. 4 times 7, 28. 28 plus 6 gets us to 34. We have to add all of them. And the popular answer, the most popular answer with 63% of the class chiming in, well, no, was C. It was C before I said that, but yeah, C is the correct answer. I'm going to leave this poll open so you guys can answer it, but let's go ahead and do this one. We've got 34 electrons. Okay, next question. Could you explain how you decide which element will be the central atom one more time? Absolutely. Absolutely. When we look at the periodic table, what I want to do is I want to answer a couple of questions. And I can kind of approach this in 2 different ways. I would say the easiest thing to do is to look at this. What is the first element written in the formula? SF4. S. That's a good start. I'm using my phone. How do we see the poll? I've already pressed on more. When you press more, you should see polls pop up as an option. And that's the polls menu, or sorry, the more menu will pop up, and underneath there should be polls. There's going to be another couple of poll questions. Maybe it toggled back. I mean, tap the screen, that might flip it around. So our first element is going to be our central element. more times than not. Our first element in the formula is going to be our typical one. Alternatively, look at what's farthest left on the periodic table. And just as a little bit of a reference, oh, between sulfur and fluorine, look at this right here and see, oh, well, sulfur is farther left. Does it matter that it's lower? It doesn't. It's farther left on the periodic table. So I'm going to go back to that slide. So I've got SF4. Boom. 34 electrons, central atom, S. And as you can see here, I have a tendency to kind of combine a couple of steps. So I drew my adjacent atoms and I drew my single bonds because I know that at very least there will be a single bond connecting these. So based on this figure that I've got right here, how many electrons have I drawn? Could somebody add that? Because I'm going to go back to my accounting table, 34 total. And then I drew 4 single bonds and I'm getting people adding in 8. You're absolutely right. So I've drawn 8 electrons in the form of 4 single bonds. I'm going to put in parentheses here, 4SB. So now I've got 26 electrons left to draw. Okay, so my next step, I'm going to go back right here. Let's see where I'm catching up. I did my total number of electrons. Got that. I got my central atom. I drew all of my other atoms around that central atom, and then I connected each one of them with a single line. Place my electrons on my outside atoms. Okay, so that's what I need to do here. So I've got 26 electrons. The next step is going to be to put those 26 electrons on my outside atoms. Okay, so I'm drawing them, and whenever I'm drawing atoms on exterior or adjacent atoms, I do them as individual dots. I don't do anything like, oh, I draw a line to represent that. So I'm going to circle the electrons that I drew outside here, just to make it a little bit easier for me to keep track of. Here's 6 electrons. Here's 6 more electrons. Can you give me a Y or an N in the chat if you follow what I've done so far on this before I proceed? And if you have an answer of no, then please let me know what it is that you're caught up on. Okay. So I'm seeing lots of Y's, which is great. I got 6 and then 6. Okay. So how many electrons are circled in green? 24. 6 plus 6 is 12, plus 6 is 18, plus 6 is 24. So I'm going to say minus 24. Okay, now give me a Y or an N in the chat if you're good with that, in the sense that you follow that. Okay, I'm erasing my circles. And now what I'm going to do is say, is this fluorine not happy? Yeah. And then, are all of my fluorines happy? Yeah, they all look the exact same. So after I've satisfied the octet of all of my adjacent atoms, I've drawn 24 electrons. 26 was the total that I had to draw. Minus 24 gives me 2. Could anyone tell me which element they think those 2 electrons are going to go onto? The central, the sulfur. Okay. Can I do that? Well, before you answer, and I'm going to end the poll that I just had up. And again, there's going to be a couple more polls, so hang tight on those. My first question is, after I've drawn those 2 electrons, I'm going to say minus 2. I have 0 electrons. Have I drawn 34 total electrons? Y or N to the chat? I have. Okay. Do each of the fluorines have a complete octet? They do. Each fluorine is happy. Looking at that sulfur, how many electrons are around sulfur? 10. Is that, well, is 10 8? No, it's not. Does that sulfur have a complete octet? No, it doesn't. But is that a problem? Oh, just a second, just a second. I got a private message that I want to address. Um, to get to a complete octet and then add a triple or a double bond as needed. Now, let me go back to this for a second. Sulfur is one of the atoms that can exceed the octet. So, to directly address, is this sulfur, is this depiction of sulfur with 10 electrons around it, is that a problem? No, it's not a problem. Now, this private message question that I got of, would it be better to do a double bond? Here's the thing with double bonds. Whenever you draw a double bond, like if I were to do this right here, this presents a little bit of a challenge. Okay. Um, One thing is, how many electrons are around this sulfur? It's still 10. So removing that lone pair and putting it as a double bond doesn't really change whether that sulfur exceeds or does not exceed the octet. So in this case, we wouldn't want to do a double bond. In addition to that, if I kept this here, well, then we'd be at 2, 4, 6, 8, 10. So now fluorine is exceeding the octet. And you might be looking at this and say, so we don't want fluorine as an element that exceeds the octet. But then you might also, and actually, so before I proceed to the next step and the next kind of analysis of this double bond, does everyone follow why we don't want to do this double bond in these depictions? Give me a 1 in the chat if you follow that, or a Y, whatever. Okay, okay. Now, whenever you introduce a double bond, effectively what you do is you then are going to remove electrons from another location. So if I put the double bond here, everyone's in agreement that this fluorine has 10 electrons around it. Well, if I do this, how many electrons does this fluorine have around it? 2, 4, 6, 8. Oh, well, fluorine's got a happy octet now. Okay, so is this a good option? Well, before let's go through and count all these up. And what I always do is I start in one location and mark it off because I'm going to count up my electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Ooh. Now I just made electrons disappear. It doesn't resolve the issue of, so drawing the double bond, long story short, drawing the double bond in this case is not really appropriate because if we were to do that and satisfy some octets, then we'd run into a problem of not drawing enough electrons. And this is a little bit complicated. So if you follow this, pat on the back. In the event that you're like, wait a minute, I was struggling with this from the jump, then don't stress about this too much because double bonds and triple bonds are kind of unique circumstances that we're not going to see too often, but we will see them. I'm just saying that it's not going to, I would be a little bit, what's the word, judicious as to when you use a double bond or a triple bond. But with that said, sulfur is an element, is an atom that can exceed the octet. Okay, can you give me a 1 to a 3? A 1 being, okay, I'm doing pretty good, and a 3 being, I'm going to have to watch this whole lecture over again. Okay. 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 Again, if you've got questions about this, I'll be available today at 11 for office hours. What we're going to do now is go and take a look at this poll question. So this is our next poll question for the day. How many single bonds are coming from sulfur? Is it one, two, three, or four? And I'll just do a quick model of our molecule. S, boom, boom, boom. F, I'm not going to draw all my electrons around my fluorine. And then a lone pair. Okay, we're going to go on to the next slide. And I'll give about 10 more seconds on this poll question, then I'm going to stop it. Three, two, one, zero. The most popular answer at about 55% was four. You're correct. Um, there are, this was just a count of how many single bonds are there. One, two, three, four. Didn't ask anything about lone pairs. But with that said, another question that you might want to anticipate would be a modified form of this. And it would be something like how many lone pairs are on sulfur? Or how many lone pairs are on each fluorine? And if the question was, well, how many lone pairs are on fluorine? Your answer would be three. There's three lone pairs on that fluorine. Okay, so there's more of that. Now, next up is ClF3. Oof. Okay, we've got how many chlorines for this molecule? How many fluorines? Okay. Now, if you look at the periodic table, you will see that chlorine and fluorine are in the same column. Okay. So one of the challenging parts about this formula in particular is which is our central atom? Now, before we get to that, let's ask the question, how many electrons do each of these roll in with? They each roll in with seven. So that brings us to a grand total of 7 electrons, 21 electrons. Could everyone give me a asterisk or a multiplication symbol in the chat if you see where we got our grand total of 28 electrons? And then a minus symbol or a minus sign if you don't see where that came from. Okay. So we have a total of 28 electrons to draw. Which is our central atom? I gave you a couple of guidelines. One guideline is typically the first element listed in the formula is going to be your central atom. Let's imagine that I said, hey, there's a molecule made up of one chlorine, or I'll rephrase it, a molecule made up of 3 fluorines and 1 chlorine. Well, then you don't have that ClF3 to lean on. And instead, you've got to figure out, well, which do I list first? Which is my central atom? And so then we're going to go back to our guideline. Our guideline is, which is our central atom? It's not hydrogen. That's not in this formula altogether. If it's the first element listed, well, if that doesn't work, that doesn't really help us. Farthest left on the periodic table, oh, they're in the exact same column. That doesn't help us at all. Least electronegative element. Okay. If you operate under the idea, and what I want you guys to do is I want you to say fluorine is the most electronegative element. Everything else is less electronegative. So fluorine is 4, and everything else is less than 4. That would be enough to pull that chlorine is the central element. Can you give me a V in the chat if you follow that, and a U in the chat if you do not follow that? Okay. Now, with that in mind, I would give you electronegativity values so you can go back to this and you can reference this. But more times than not, if these first two options, 1 and 2, don't help out, you're going to be able to look at an extreme and say, well, something other than fluorine is the central element. Okay, so now what we've got is chlorine. Chlorine as our central element, Cl. Then we have F, F, F. 2, 3. 28 minus 6. Does everyone follow? Give me a 1 in the chat if you follow, and a 5 in the chat if you do not follow this math right here. Okay, so we got 22 electrons left to draw. The first place that we go is our outer electrons. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, 18. Minus 18. Okay, so now I've got 4 electrons left to draw. Okay, so I've got 4 electrons left to draw. Oh boy. Well, if I put 2 here, gets me 2, so now I have 2 electrons left to draw. Can everyone give me a 7 in the chat if you follow what we're looking at right here? Okay. Now this is a situation where it's like, oh boy. Did it get a lot more complicated? Now, this might be an instance where you're like, oh, this is maybe a good double bond opportunity. Okay. Chlorine is an element that can exceed the octet. And if we do this, it does exceed the octet. But if we do that double bond, that doesn't resolve the problem of we have too many electrons to draw. So this is a place where you got to go, oh, wait, dot, 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 dot. We put 2 lone pairs of electrons on there. Now, that might seem like, oh, secret option C, we can do that. Yes, you can. First question, can chlorine exceed the octet? Yes, it can. Given the option, do we want to make fluorine an element that doesn't exceed the octet? Well, do we want to try to make it exceed the octet? Or do we want to just add another lone pair of electrons and see that as, okay, well, this has a complete octet? We want to go with this. How many electrons does this chlorine see? 2 lone pairs, 3 bonded pairs, 10. How many electrons do each one of our fluorines see? You're right. Okay, so now we are going on to our last poll question for the day. And our last poll question reads, if we have 8 electrons surrounding each fluorine, how many total electrons have we drawn? Okay, so this is kind of the process. Cl, F, 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 boom, 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 boom. We had 28 total to draw. At this point in time, without drawing any lone pairs of electrons, how many have we drawn? Well, we did that math. We've drawn 24. Hey, 24 electrons have been drawn. Did this a little bit out of order because we went through the process of drawing this molecule, and this poll question was kind of an intermediate question of like, well, how many have you drawn? Could everyone give me a 6 in the chat if you follow where that came from? And you understood this part of the process. Okay. I'm going to leave that poll question up for just a minute for anyone to finish that. And now we are on to our last molecule, SO2. Now for SO2, I'm going to go back and go through this whole process. Okay, sulfur and oxygen are both in group 6. So they are both coming in with 6 valence electrons. And so what I'll do is say Sulfur brings 6. Each oxygen brings 6. So we're talking about 2 times 6, 12 electrons, plus 6 electrons, gives us a grand total of 18 electrons. Does everyone agree with that statement? Okay. Which is our central atom? They are in the same column. S happens to be our first element that's listed, SO2. Okay. Now let's complete the octet. So this gives us our electron counting, 18 minus 4, not 6, minus 4. That would be 14 electrons. Okay. So now what I'm going to do is go boom, boom. 6 electrons have been drawn around that oxygen. So now I'm down to 8 electrons. 2, 4, 6 minus 6. That gets me 2 electrons. Okay. Uh-oh. So I say uh-oh because I had 2 electrons left to draw. So I drew 2 as a lone pair of electrons, and that gets me to 0. Okay. Now, a Y or an N to the chat. Does oxygen have a complete octet? It does. Y or N to the chat. Does sulfur have a complete octet? No, it does not. Okay. This is tricky because, well, sulfur can break the rule by exceeding the octet. Sulfur is not going to go under. Okay. So this is a place where we don't have enough electrons to draw to get everything to complete the octet. We can't go into like an electron deficit. So instead what we do, and I'm going to put a little note here, not enough E for structure. Okay, so I'm going to put a box around this. And now I'm going to restart it. S, O, O. And what I'm going to do is put 2, 4, go to this exact same structure. Oh, there we go. And this is where I have to make a minor modification. This is where I'm going to bring in something like a set of double bonds or a double bond. Whenever I do this right here, okay, this model right here shows that sulfur, well, it has a complete octet. But does oxygen have a complete octet? No, it's exceeding. So I'm going to drop those 2 electrons. Okay, so now, does oxygen have a complete octet? Y or N to the chat. It does. Does sulfur have a complete octet? It does. And this oxygen has a complete octet. But how many electrons does this model show? It shows 2, 4, 6, 8, 10, 12, 14, 16, and 18. Okay. So at 18 to draw, and this will ultimately work for us. Unless I miscounted. Did I miscount? No, I think I'm good. Okay. So that's where we've deployed a double bond, and we're good to go. Okay, now poll question's done. The popular answer for this question was A, great. We'll do a couple more examples, or we'll do more examples of this process, but practice this, and I hope that you guys have a great Thursday and a great weekend. I will see you on Tuesday. Deal? I'm going to stop the recording.